All right. Time's up. Time's up. Okay. Now let's start the course. So we are going to teach you electrodynamics, as you know, and I'm actually before we start this course, I'm actually going to tell you what content we are going to learn in this course. First, introduction, a brief introduction, and vector calculus. This is what we're going to cover today. Second, EM, which signifies electromagnetism. Maxwell equations. Maxwell equations, as we know, we actually have already learned electromagnetism, right? And we actually learned Maxwell's equations in electromagnetism. As we know, the famous four equations, del cross E, del cross E, del dot E, del dot E, right? The four equations of electromagnetism, which are called Maxwell equations. These are the most important equations in electromagnetism. Also, in electrodynamics, actually, in our course. So this is the basics. Yeah. Third, I'm gonna teach you a little bit of electrostatics, and then the boundary value problems, and then the magnetostatics, and EM wave and propagation, and then EM wave and radiation. So what's the difference between propagation and radiation, if any one of you know? Well, propagation means the wave propagates. It travels, goes in front, in this way, in other ways, right? It propagates. And radiation actually makes what more important? Radiation makes the transfer of energy more important than propagation. So propagation is to propagate information, and radiation is to radiate energy. It's to radiate energy, right? That's the difference between propagation and radiation. So last in this course, in the electrodynamics course, I'm gonna teach you a special theory of relativity. We're not gonna teach like general theory of relativity, but only special theory of relativity. I guess if you guys are here for physics, and you guys are physics major, I guess you're probably more or less interested in, or at least you were more or less interested in special theory of relativity, right? Because that probably drove many of you here. That actually drove me into the physics major. Yeah, because this is very interesting. Because I guess you must have watched quite a lot of sci-fi movies, and how can time become slower? How can time become faster? That's so interesting, right? Yeah, this is what becomes interesting when we teach this electrodynamics. And you will actually know why we teach special theory of relativity in electrodynamics. Because when we learn EM wave radiation, we are going to learn a little bit like the delayed potential and these kind of things. And you know, they are not at the same time. You think they happen at the same time, but they're actually not, right? Yeah, that's what makes electrodynamics interesting. All right, these are the contents of our course. Now let's start our introduction. Now we have a creator here. Oops. Anyway, let's start the course from introduction to electrodynamics. So as we know, electrodynamics, or ED for short, I guess that's not a good abbreviation. Electrodynamics, right, is a core course of present-day physics major students. It means that it's a major course. It's required. We have to learn electrodynamics in most physics major in the world, I guess. In every university in the world, we have to learn this course. So that's very important. Together with quantum mechanics, they are, I guess, one of the most difficult courses in physics major, I could say. Well, I think it's difficult, to be honest. I don't think it's difficult. But anyway, yeah. What are, for example, the applications of this course? For example, electrodynamics can be applied to radar technology or laser technology. Well, I'll tell you why later. And then, for example, plasma physics, or astrophysics, or space physics. Space physics is actually what I'm working on for my master degree, for my PhD, and well, I've not been working for. I'm lazy. I've not been working for it long enough. If I work, I still have to work on space physics. So space physics is a major which is based on plasma physics. Meanwhile, plasma physics is based on electrodynamics. So electrodynamics is actually a basis of plasma physics, which is further a basis of what I study, space physics. So as you know, I'm here. It's useful for me at least. I don't know if it's useful for you guys, but anyway, it's useful for some field, I can say. All right. As I told you that this is together with quantum mechanics, this is one of the most difficult courses in physics major. Why? Why is it difficult? Why? Because it has many requirements. For example, we require so many math courses, including advanced mathematics, including linear algebra, including the mathematical physics. I guess mathematical physics is much more complicated than linear algebra and advanced mathematics because it's a combination, right? Second, physics courses. The ED, or to say electrodynamics, let's not make this abbreviation. Okay, just call it electrodynamics. Electrodynamics is also based on a physics course which is called electromagnetism, which I guess we have already learned in the second year of our university. It's also one of the major courses in physics major. Well, none of these courses are easy to learn, and I know them well. None of them are easy to learn, I know. And our course, Electrodynamics, is based on all these courses. So I know it's difficult, but just try your best. I'll try my best too, but but you guys also have to try your best to get as many as possible. As for the equations, I guess maybe just remember, maybe just to recite the equations. But don't feel it as a burden. Don't think, oh, it's so difficult. I don't understand. And I also don't understand some of them. Don't worry, because I know it's difficult. Just recite as many as possible. Just consider you're not in science, you're in arts, and you have to recite, for example, something like for example, philosophy, in whatever, in economics. You also have to recite many things. Just recite instead of words. Recite the equations. Just try to recite that, and don't take it as a science course. Yeah, if you think it's too difficult. All right. Now, those are the basis of our course, electrodynamics. And then, let's come to the history of electrodynamics. Let's try to understand how this course has been developed. Open the book. I guess you don't have the book, but I have printed out what is necessary for you guys. I guess you probably don't have a book, but don't worry. Just look at what I printed out for you. So, first, in 1785, Coulomb, a French scientist, has found a law which is known as Coulomb's law, right? I guess you guys know it. Coulomb's law marks the beginning of research of electromagnetism. As I told you that electromagnetism is the basis of electrodynamics. So Coulomb first found this Coulomb's law in 1785. And then this is Coulomb, this guy, right? Yeah, this guy. That's Coulomb. And then in 1835, Faraday, an English scientist, physicist, of course, found Faraday's law and a couple of more. I guess he found many other theories and laws too. Let's see what Faraday has been doing. He was studying the effect of time-varying current and magnetic field, right? From Faraday, parity, we know that now electric current can generate magnetic field, and magnetic field can in turn generate electric current. I mean, changing magnetic field and changing current, right? That's what parity called. And then in 1864, Maxwell, we all know this guy. Maxwell is this guy, right? This guy is Maxwell. Maxwell found what is known as, he probably didn't found, but he summarized what is known as Maxwell's equation, right? And this is the most important equation, or these are the most important equations in electromagnetism, right? These are the most important equations in electromagnetism. And also in our course, which is electrodynamics, right? And then in 1888, Hertz, this guy, this German guy, Hertz, he proved the existence of EM wave, which was like established by Maxwell, right? And then in 1905, this guy is even more famous than all of those because this guy is, we know this guy quite well. He's probably the greatest scientist in the 20th century, right? Yeah, his name is Einstein. Can we say German? Well, okay. He's a Jewish guy, right? He's a Jewish scientist who has established the special theory of relativity. And this is actually what is very interesting. It actually, it actually proved that Newton's law were wrong, right? Or at least wrong. Like if we consider higher speed, if we consider, for example, micro scale, right? So this is a brief history of our course, electrodynamics. All right, I guess those are the basis of the introduction. Well, after the introduction, let's have a look at vector calculus. Let's come to math. Now it's math time. Okay, we know. Some of you probably don't know, but I hope you know. I hope you know that a vector is written like this, with an arrow above a letter. This is a vector, right? A vector is written like this, and a vector is different from what we know as a scalar, right? A vector is different from what we know as a scalar, which is here. A scalar is written without, we can also write A, right? We can also write A, but here, we would like to write 5. I'll tell you why later. I'll write 5 here, I'll tell you why. And this 5 is a scalar. Yeah, it's a scalar. And what's the difference between a vector and scalar? All right, it's written like the PowerPoint. A vector has both value and direction. Value and direction, right? A scalar has value but no direction. No direction, right? A vector has value and direction, but a scalar does not have a direction. How do we understand this? Yeah, for example, a scalar is easy, right? For example, the density of anything, the density of Y density, I'm probably made of water, right? Everyone is. The density of water in our body, for example, maybe not water, but the density of meat. Okay, anyway, the density, right? It does not, obviously, the density does not have a direction. The density, right? Density does not have a direction. But, for example, oh, I'm running to the course, I'm running to the class, I'm running. What is my speed? My speed, I'm running toward a direction. I'm not only running at a speed, but also it has a direction, right? Yeah. So the velocity I'm running, the velocity is a vector. And for example, the density is a scalar. It does not have a direction. Yeah. This is the difference between vector and scalar. As for vector, we can also show a vector like this. Vector A equals AX, vector EX, plus AY plus AZ, EZ. What are these EX, EY, EZ? Yeah, I think we are already third year students in physics. You probably know it, but EX, EY, EZ, they are unit vectors of what? Of a Cartesian coordinate system. In a Cartesian coordinate system, yeah, EX, EY, EZ is, for example, we have a Cartesian or Cartesian coordinate system, which is like this, right? X-axis, Y-axis, Z-axis. Our Cartesian coordinate system is like this. For example, we have X-axis like this, and Y-axis is vertical to X-axis, and Z-axis is vertical to both X and Y. Must be here, right? These three vectors, or these three axes, are vertical to each other, and this is called a Cartesian coordinate system. And we can use it to signify our space in what we live in, right? So, for example, EX is a unit vector in the direction of X, and EY is a unit vector in the direction of Y. EZ, same thing in the direction of Z, right? And this is how we show a vector like this using three unit vectors. Why is it good? Because in this case, we can know the X component of the vector A, the Y component of a vector A, and Z component of vector A. Why? Because, for example, we have A here, and AX is the projection of A to X axis. AY is projection of A to Y axis, right? Right? And then it becomes a vector or scalar. A scalar, right? Scalar. Yeah, that's why it's good. Okay, now I guess we know it because we're physics major students. And then let's have a brief revision of the length of a vector. A length is shown like this, right? A with an absolute value symbol like this, right? It's the length of the vector A is the square root of AX squared, AY squared, AZ squared, right? I'm not going to write it because I guess you guys know it. No. So, unit vector, which I told you about the unit vector in X direction, Y direction, and Z direction, right? But a unit vector is a very important physical term. Like, what is a unit vector? It's written like this: E(n) vector, and equals the vector, for example, vector A, divided by or over A's length. Why? If we divide the length of the vector, then it becomes a new vector with the length 1. So, unit. What is a unit? For example, the unit of mass is kilogram or gram. The unit of, like, for example, what? Length? Meter, for example, 1 meter. What about 2 meters? 2 meters. Meter is a unit of length. Gram is a unit of mass, right? So we say 3 grams, 3 times 1 gram, which means unit must be 1. Unit is something which has a value of 1. And a unit vector is 1 with a direction. With the direction of the same direction of the vector we are considering. That's the unit vector. So here are the basic calculus of vector calculus. For example, vector A plus B equals B plus A, as we all know, and A plus parenthesis B plus C is parenthesis A plus B plus C. And eta, suppose eta is a number, and a number times a vector. If the number is larger than 1, for example, it makes the vector longer in the same direction. It does not change the direction. We learned it in, of course, in high school too, in high school maths. We also learned it in, for example, linear algebra in the university, that we multiply a number to a vector. It does not change the direction, but it makes it either longer or shorter, or it changes the direction, right? If eta is minus, if eta is less than 0, it changes the direction of the vector, right? So, dot product. Now let's go to dot product. As we know, A dot B, vector A dot vector B. We learned it in high school math or linear algebra. It equals ax bx plus ay by plus az bz, right? That's the dot product. The dot product makes vector a scalar. It makes vector a scalar, right? Yeah, it's a scalar. There's no vector symbol anymore, right? It's also equivalent to a's length, b's length, cosine alpha, where this is a's length, b's length, where alpha is the angle between vector A and B, right? So, how do we understand this? How do we understand the angle, cosine the angle between A and B? So let's draw geometry. Let's draw its geometry. For example, we have vector A, which is here. And for example, we have a vector B here. So let's just maybe have a look at this. B cosine alpha. And where alpha is the angle between the two vectors, right? And then B cosine alpha means B project to the direction of A, which means B cosine alpha equals to this length, right? This length. This length is B's length project to the direction of A, right? So it means A's length, B's length project to the direction of A, right? Or B's length times A's length projection to the direction of B. Yeah, that's the geometric meaning of A dot B. That's why it's A length, B's length, cosine alpha. And then let's have a look at this cross product. Alright, as we know, okay, let's clear these parts. As we learned it in advanced mathematics, I guess we have learned it. A cross B can be written as, what is this? Can be written as a third order determinant, right? This is a third order determinant, like this, right? Yeah, and the first line should be, the elements here in the first row should be EX, EY, EZ. I mean, of course, they can also be written as vector I, like this vector J, or vector K, right? They symbolize the same thing, either I, J, K, or EX, EY, EZ. Both of them mean that the unit vectors in the Cartesian coordinates, right? That's what it means. And the second row should be A's X component, and A's Y component, and A's Z component. And the third line should be Bx, By, Bz, right? And this is called the third order determinant. as we learned it in linear algebra, right? We learned it. It's called a third order determinant. And how do we expand this third order determinant? The product of these three plus the product of these three elements plus these three, right? Minus these three, minus these three, minus these three, right? This is how we expand this third order determinant. And also, I'm gonna tell you why, but its geometric effect we'll see later. But I can tell you that A cross B's length. First, alright, you know A cross B is a vector. It's not a scalar anymore. We know that the dot product A dot B becomes a scalar, but here A cross B is still a vector, right? Now I can tell you that A cross B's value, or to say its length, is A's length, B's length, sine alpha, where alpha is the angle between A and B. I can tell you why. Alright, let's draw Cartesian coordinates first. This is a Cartesian coordinate. And we can make A, or to say, before drawing this Cartesian coordinate, we have two vectors, vector A and vector B, right? How do we choose the Cartesian coordinate? The two vectors can be anywhere, but we can always parallelly move one vector so that the two vectors join together from the same starting point. For example, like this. We can always move any vectors parallelly. That's what we learned in high school. For example, we join these two vectors, and two lines always form a plane. Two lines always form a plane. And we can choose one of the vector, for example, vector A's direction as x-axis. And we choose y-axis so that B falls in the plane of xy. We can choose A in the direction of x-axis, and we can choose B so that B falls in the plane of xy. And in this case, we know A is here, right? A is in the direction of x. And B, vector B is in the xy plane, right? B is in the xy plane. And we know A cross B, as we learned in high school math. A cross B is always in the direction of, which is vertical to both A and B. And, well, and we use our right hand, which is known as right hand rule, right? We use our right hand. Oh, we know that because A is here in the x-axis direction, B is here in xy plane. So we use our right hand. We know that A cross B must fall in z-axis because we choose B so that B falls in the plane of xy. And z is always vertical to the plane of xy. So A cross B must fall in z-axis. Now let's have a look. We have this definition of A cross B, right? And now let's expand it. Let's try to write it. Write A cross B. First, we know EX, EY, EZ, or IJK, right? It's easier to write. So let's write IJK. It's easier, right? Otherwise, EX, EY, EZ. It's more complicated. And now we have A here. We have A here, but A does not have component of Y and Z because A falls in x-axis. So A does not have Y component or Z component. Similarly, B does not have Z component because B falls in xy plane. Because, for example, we have two vectors. We can always join the two vectors together. And the two vectors always form a plane. We choose one as x. We choose one y so that B falls in xy. That's why B's Z component is also 0. And A only has x component. So A's x component equals to its length. Equals to its length, right? Because it only has x component, it falls in the direction of x-axis. And b, let's have a look at b. b falls in the xy plane, so this is b's length, right? B's length, let's suppose this is alpha. The alpha is the angle between a and b, right? And b's x component should be b cosine alpha, right? b cosine alpha. And b's y component as b's projection to the y direction. This is equivalent to, this is equal to b sine alpha, right? b sine alpha. B's length sine alpha, right? Right? And where alpha is the angle between a and b, right? So b's y component is b sine alpha. X component is b cosine alpha. And this is a third order determinant. Third order determinant. And let's expand this third order determinant according to, let's see, it has so many zeros. This determinant has so many zeros. So, how do we expand it? Let's choose this column, the third column. Let's try to expand according to the third column. So, as we know, the third order determinant is equivalent to, okay, all right, there's only one element, k, vector k, which is not zero in the third column. So how do we expand it? First, minus one's, okay, this is the first row, third column, 1 plus 3, right? This is how we expand it. 1 plus 3 times, now we have a second order determinant. Now, right, we have k times a second order determinant, where the second order determinant is these two product minus these two product. And this two product, there's another zero, which means this product is also zero, which means we only have this left, this product left. And this is equivalent to, this is equal to a length, b's length, sine alpha, right? Sine alpha. And don't forget to multiply this, k. K's direction. Or to say, or we can write, instead of k, ez, right? ex, ey, ez. Ez is easier to understand because it's in the direction of z, right? It's the unit vector in the direction of z. Now we know a cross b. A cross b's value, or to say its length, is a's length, b's length, sine alpha, where alpha is the angle between a and b, right? And which direction is a cross b? It's in the direction of ez. It's in the direction which is vertical to both a and b, right? Now we can get it, right? Minus 1 to the 1 plus third, it's 1, right? It's 1. We can remove it. Now, this is a cross b. All right. I guess we can. All right. I guess that's all for today. We can teach probably next week again. All right. Thank you all.